Hello, welcome to My Easy Statistics. In this video, we are going to discuss about how to create a regression model in PLSEM, and we are going to discuss about creation of the model, and after the creation we will even discuss in detail the interpretation of the results also. First we will discuss what is this regression analysis. This is a linear regression where we have one dependent variable and more than one independent variable. For example, let us discuss this example where we have student performance. This is an Excel file. Okay, in this student performance file you can see there are totally 5 variables are there. In these 5 variables, the first variable is final exam score. This is the marks which the student have scored in an exam. This is a dependent variable, and this dependent variable is getting impacted by 4 independent variables. The first one is practice exams, means the number of exams the candidate has taken in the semester. And the second one is hours studied, means number of hours they have kept per day for studying. And the third one is a previous quiz score, means how much score they have got in the quiz. Okay, and the fourth one is class attendance. This is the amount of classes they have attended in that particular semester. So in this regression analysis we are trying to understand, we are trying to analyze how these 4 independent variables are going to impact the dependent variable. This is the linear regression where we have only one dependent variable. Now what we will do is I will go to PLS SEM. In that we are going to first import this student performance Excel file first, and we will draw the model and we will do the analysis. At last we will discuss in detail all the interpretation part. Results totally will be discussed. So we will start SmartPLS. In the SmartPLS, first we are going to import the file. So open this here in this project called PLSEM training. Okay, right click on this and click on this import data file. Now this data file is on the desktop where we have student performance. Click open. Now here you can see all the 5 variables are here, and these data are metric data. Okay, so metric data already we have discussed. For final marks, minimum marks 50 marks, maximum 100 marks. So in this way all the details are given here. In this data we don't have any missing data, so we are not going to do any sort of missing management of the data here. The total data here is 200 samples, 200 cases we have. Okay, the project name is PLSEM training and the file name will be student performance. Simply click import. Now once I click the import, the file is got imported. You can see these are the indicators. Indicators are nothing but the variables here. And if you click here, we'll see the correlation between these indicators. And if you want to see the raw data, you can click this button, radio button called raw data. This is all about the raw data. Now what you are going to do is we are going to now create the model for this regression analysis. Okay, so in this PLSEM training, now what you will do is you will click here and say create data or a new regression model. Once I click regression model, now you can see the project is PLSEM training. Model type is regression. We have different type of regressions. Here I am selecting regression, and the name we want to give is regression model. Okay, and just click save. Once I click save, now we are going to go for the SmartPLS canvas where we can draw the model in this place. Right, now first select the data which you want to use for this model. The data is student performance. Now you can see we got all the 5 variables. First what we do is we will select this final exam score. We will simply click it, drag it onto the canvas. Once I drag it to the canvas, you can see final exam score and with the intercept. Now let me make this intercept to the right side. Now let me take all the independent variables, shift and select all the 4 independent variables and select them, drag and drop on the final exam score. Okay. Now you can see we got all the 4 independent variables. Now let me make it to left side. Okay, now this is a model which we got. We have one dependent variable, final exam score, it has intercept, and 4 independent variables are there. You can resize this: previous quiz score, practice exam, hours studied, and classes attended. So this is a final exam score. Now what we will do is we will save the file. Okay, once after saving, let us go for calculation part. Click this button called calculate. Okay, once I click calculate, now we have different type of calculations in regressions again, like regression analysis, which is a linear regression we are going to do here. Later we are going to do logistic regression. Okay, so first let us click this regression analysis. Once you select regression analysis, you can see test type, two-tailed test you want to do. Significant level is 0.05, that is 95% confidence interval we are going to take. Standard error type is a normal standard errors. Now click start calculation. Now once we click start calculation, now we got the analysis. Now this is a screen where we can see the model here, where class attendance, hours studied, practice exams, and previous quiz score, how much they are impacting the final exam score. You can see these are called as path coefficients. We will discuss all these values one after another. Now you can see these are standardized coefficients. If you want to see unstandardized coefficients with p-value or standardized coefficients with p-value, we can select what are the options we want. For example, I want to see standardized coefficient with p-value. We'll get both values. See, all are zeros. P-value less than 0.05 is called significant. So in this case, class attendance, hours studied, practice exam, quiz score, everything is significantly impacting. You can see on the final exam, you can see 0.649. This is R square value. In place of R square value, if you want to see Durbin-Watson test also, you can see that value here. If you want to highlight the path which is impacting more, you can click here. Previous quiz score is impacting the highest one. The bolt, it is having more bolt, it means it is impacting more. Now what we will do is we will discuss all these interpretation values in a sequential form, starting from summary coefficients. In the final, you can see in the left side, final results. In this final results, we have summary coefficients. Now we will discuss all these values in a systematic way, in a detailed way we are going to discuss. Summary coefficient tables contains unstandardized coefficients, standardized coefficients, standardized error, t-value, p-value, and upper and lower bounds of the confidence interval for the coefficient estimates. The unstandardized coefficient show the actual change in the dependent variable for a 1 unit change in the independent variable, while the standardized coefficient show the change in the dependent variable relative to the standard deviation of the independent variable. Standard error is an estimation of the standard deviation of the sampling distribution of the coefficient. It helps understand the precision of the coefficient estimate. Smaller the standard error suggests more reliable estimates. The t-value is a ratio of the coefficient estimate to its standard error. It's used to test the hypothesis that the coefficient is equal to 0 in the population. A large absolute t-value indicates a more significant relationship between the variables. The p-value is associated with the t-value and indicates the probability of observing the obtained t-value if the null hypothesis is true. A small p-value, typically less than 0.05, suggests that the coefficient is statistically significant. 2.5 and 97.5 are the low and upper bounds of the confidence interval for the coefficient estimate. The confidence interval gives us a range within which we can be reasonably confident that the true population confidence lies. Now we will discuss the interpretation of the results of the impact of independent variables on the dependent variable. We'll start with the class attendance. The unstandardized coefficient for class attendance is 0.111, this one, which means that 1 unit increase in class attendance is associated with a 0.111 increase in final exam score. The standard coefficient is 0.181. Okay, which means that the change in final exam score is 18.1% of the standard deviation of independent variable class attendance. The p-value is 0.000, which means that the relationship is significant at the 0.05 level. This suggests that class attendance is a weak predictor of final exam score. Now we will see the next one, that is hours studied. The unstandardized coefficient for hours studied is 1.160. Okay, which means that 1 unit increase in hours studied is associated with a 1.16 units increase in the final exam score. The standardized coefficient is 0.227. which means the change in the final exam score is 22.7% of the standard deviation of hours studied. The p-value in this case is also 0.000, which means the relationship is significant at 0.05 level. This suggests that the hours studies is only moderately predicting the final exam score. The third one is practice exam. In this case, the unstandardized coefficient is 1.647, which means that a 1 unit increase in practice exam is associated with a 1.647 increase in final exam score. The unstandardized coefficient is 0.282, which means that the change in final exam score is 28.2% of the standard deviation of a practice exam score. The p-value is 0.00, which means that the relationship is significant at 0.05 level. That suggests the practice exam is moderately predicting of the final exam score. The final one is previous quiz score. In this case, the unstandardized coefficient value is 4.310, which means that 1 unit increase in previous quiz score is associated with 4.310 units in final exam score. The standardized coefficient is 0.444, okay, which means that the change in final exam score is 44% of the standard deviation of a previous quiz score. The p-value is 0.00, which means that the relationship is significant at 0.05 level. This suggests that previous quiz score is a strong predictor of final exam score. So all the 4 independent variables are significantly impacting final exam score. But in this, the previous quiz score is impacting the highest one. The least one is class attendance. Now we will discuss summary of ANOVA. This ANOVA table shows the results of statistical tests that is used to determine whether the independent variable in the model are significantly related to the dependent variable. In this case, the null hypothesis is that the independent variable in the model are not significantly related to the dependent variable. The p-value of 0.000 is a less than 0.05 significant level. So we can reject the null hypothesis. This means that the independent variable in the model are significantly related to the dependent variable. The result shows that the f value of regression is 90.313, which is significant at 0.05 level. That p-value is 0.000. This means that the independent variable in the model are significantly related to the dependent variable. The mean score for the regression is 2884.277, which is much larger than the mean square of the error, that is 31.936. This indicates that the independent variables in the model are able to explain a significant amount of the variance in the dependent variable. Overall, the results of the ANOVA table suggest that the independent variable in the model are significantly related to the dependent variable, and the model is a good fit of the data. Next, we will discuss about R square. Okay, in this R square table, first we will discuss R square. This is the amount of variation in the final exam score, that is latent variable, that is explained by the independent variable. The R square value of 0.649 means that 64.9% of the variance in the final exam score is explained by the independent variables. This is a good R square value, which indicates that the model is a good fit for the data. This is the R square value adjusted by the number of independent variables in the model. The R square adjusted value is 0.642, is slightly lower than the R square value of 0.649, but it is still a good R square value. The next one, the important one, is Durbin-Watson test. Durbin-Watson test is used to assess the presence of autocorrelation in the residuals of the model. The Durbin-Watson test of value 0.925 is close to 2, which indicates that there is no autocorrelation in the residuals. This is a good sign, as it means that the model is not overfitting the data. Now we will discuss this collinearity statistics. The collinearity statistics is discussed with VIF. VIF stands for variance inflation factor. This value is a measure of how much collinearity there is between an independent variable and the other independent variable in the model. A VIF value of 1 indicates that there is no collinearity between the independent variable and the other independent variable. A VIF value greater than 10 indicates that there is a high degree of collinearity between the independent variable and the other independent variables. The VIF value for the independent variable in our model are below 1.7. We can see here all the values are below 1.7, which indicates that there is no significant collinearity between the independent variables. This is a good sign, as it means that the independent variables are not too highly correlated with each other. Now we will discuss about residuals. Residual values are the difference between actual value minus predicted value. Okay, so these are the residual values for the final exam score. Next is descriptive values. So descriptive values explains about the mean, median, okay, and the standard deviation of the final exam score. We will see QQ plot. The QQ plot is a graphical way to compare the distribution of a set of data to a theoretical distribution. In this case, the theoretical distribution is a normal distribution. A good QQ plot will show the points lined up closely along the line. This means that the distribution of the data is similar to the theoretical distribution. In the QQ plot, the points do not line up close to the line. Instead, there is a clear deviation from the line at the bottom end of the plot. This indicates that the distribution of the data is skewed to right. Now we will see residual histogram. A good histogram of residual will show a bell-shaped curve with a peak at 0. This means that the residuals are normally distributed and that there are no major outliers. The histogram does not show a bell-shaped curve. Instead, it is skewed to right. This indicates that the residuals are not normally distributed and there are some outliers in the data. The outliers in the data are likely the lower scored students. This is because the model is not making accurate prediction for low scored students. As a result, the residuals for low scored students are larger than the residuals for the high score students. Next we will see about residual autocorrelation plot. It shows the correlation between the residuals from a linear regression model at a different lags. A good residual autocorrelation plot will show a random scatter of points around the line 0. This means that there is no correlation between the residuals at the different lags. This is the line at 0 and the data must distribute uniformly around the line. The residual autocorrelation plot do not show a random scatter of point. Instead, there is a positive correlation between the residuals at lags 1 and 2. This indicates that the residuals are correlated, which is a problem. The correlation between the residuals at lags 1 and 2 suggests that the model is not capturing all the variation in the data. This is because the residuals at lag 1 are related to the residuals at lag 2. As a result, the model is not providing an accurate representation of the relationship between the independent and the dependent variable. Overall, the residual autocorrelation plot indicates that the model is not capturing all the variations in the data. This is the problem that needs to be addressed before the model can be used for making reliable predictions. Now we will discuss about the predicted values. These are the predicted values for the final exam scores. Okay, and if you see the descriptive, these are the mean, median and the standard deviation of the predicted values of final exam score. Now we will discuss about predicted versus actual values. Now we will discuss this predicted versus actual values. The scatter plot shows the relationship between the predicted and the actual final exam score for a group of students. The predicted values are on the y-axis and the actual values are on the x-axis. The line that goes through the middle of the points in the regression line, which represents the perfect prediction. If you draw a line here, this is called as a prediction line. The points in the scatter plot are all above the regression line, which means that the predicted values are higher than the actual values. This suggests that the model that was used to make the prediction overestimated the final exam score for this group of students. There are a few points that are further away from the regression lines than the others. These points may represent outliers or data points that are not well predicted by the model. It is important to investigate these points further to see if there is something about them that makes them different from the other data points. Overall, the scatter plot shows that the model that was used to make the prediction overestimated the final exam score for this group of students. There are a few outliers that may represent the data points that are not well predicted by the model. So this is all about the predicted versus actual values. Now we will discuss about predicted versus residual values. This chart shows the predicted value of the final exams on the x-axis versus the residuals on the y-axis. The residuals are the difference between the actual final exam score and the predicted final exam score. A good model will have a random scatter of residuals around the line y is equal to 0. This is a line which is called y is equal to 0. This means that there is no systematic pattern to the residuals and that they are not correlated with the predicted values. In the image, the residuals are not randomly scattered around the line y is equal to 0. Instead, there is a positive correlation between the residuals and the predicted value. This means that the residuals are larger for higher predicted values. This is a problem because it indicates that the model is not making accurate prediction for higher score students. So this is the graph for predicted versus residuals. Now let us discuss this Bruce-Pagan test. This Bruce-Pagan test is used to assess the presence of homoscedasticity in a regression model, which means that the variance of the residuals does not change across different levels of the independent variables. The test score of 16.979, it measures the strength of evidence against the null hypothesis that the residuals are homoscedastic. The lower p-value of 0.002 indicate that there is significant evidence to reject the null hypothesis of homoscedasticity. It means there is no homoscedasticity problem in the data. This is a complete interpretation of the results of regression analysis. Now in the next video we will discuss about logistic regression.